Okay, so it was much more than a day, and I apologize for that. And taking on from where I left this video, so now as we have defined the the system and we know what point we are tracing, let's do some equation curves to find it. So for that purpose, I will make another sketch so not to mess up. And our coordinate system is x, y, and uh, um, our point is here, and the angles are basically x to y. So first thing what we will do is we will make an equation curve for this point. So how this point moves when this system rotates. So we know that, and obviously we will make a equation in relation to the coordinate system of a stationary gear, that is the blue one. So this is quite simple trigonometry, and we will use explicit equation curve for x and y from the parameter t. The parameter t is a parameter, and we will use our input angle as a parameter. Our input angle in this case is the angle that the center of the second wheel traveled around in its movement around the other wheel. So this will be equivalent of our input angle. And now, how do we find the curve for that? So obviously, this is a very simple trigonometry. There is a constant distance of 2r, and x is 2r multiplied by sine or cosine of this angle t, and the other one is the other way around. So let's say which one is which one. I will just try. So it is 2 times r times sinus t, and the other one is 2 times r times cosinus t. I'm not so sure if sinus and cosinus because I didn't prepare. And now the boundaries of the t. So t is from 0 to, we know, to 45 degrees, and now we have to understand that t is actually a unitless value. However, if a formula or a function used requires default units, like for example trigonometry functions, sinus and cosinus, then by default the t will become a unit value instead of unitless value. But in other cases, t will still be unitless. It's quite confusing, so what I found is best to always assume t as unitless and explicitly make it a unit value of units by multiplying unitless t by single unit. So in this case, and as you can see, this didn't. So let's see. I will for now. So you see, this doesn't throw an error if I use t that is unitless in a sin function, and it actually assumes t to be degrees rather than radians that are unitless by default. I understand that this may be a little bit confusing, because it is confusing for me many times, because I already had many problems with equation cures. But for now, and when I use t and t multiplied by a unit, it doesn't also give the error. So t, as you can see, is either unitless in here, or I'm not so sure what is opposite of unitless, but or unit. So this t is let's say t degrees, and this t is t unitless, and this may actually come confusing when, for example, some functions requires linear units for some reasons, and then if you plot t and you are using imperial unit systems, then still it will assume t as millimeters, and then it is confusing. So if you are using explicit equation curves, always, this is a good practice, so you can obviously do what you want, but my advice is to always explicitly define t as a use t as a unit less, and multiply it by proper unit for given function, if you can basically follow my my explanation here. And but if any questions, please post. So now we have this preview of the function. So by accident, I just selected sin and cosine correctly. So I will now save it, so then it doesn't break more than I need to. And I will also change the format so we can clearly see. So this is, as we can clearly see, a correct, where is it? Okay, a correct trajectory of this point. I could probably move it a bit. So this curve, and now from this point we need this point. So let me move it a bit. Okay, so now we know that this point is in constant relation with this point and this line, because this angle is equal to this angle. So we now need a formula for basically this x and this y coordinate. So because this radius is constant, it equals a, and from vertical, so from our coordinate system, this angle we know, and also this angle from vertical, I will maybe add the vertical line. I will add the vertical line here. And this vertical line will be always vertical. And we know that angle from here to here is actually this one. So as you can see, we have fully defined geometry and we know it. You know what? I will just make this curve in the other sketch, so for simplicity of presentation. Two times r times sin t1 deg multiple deg r2 is 2 times r times cosinus t multiplied by 1 deg and 0 to 45. So now I can drag it and they have this curve in the same file. And now from this coordinate to have x of this point, we need to subtract this value, and we have to subtract this value. So where is this equation curve? So I will make another one. 2 times r times sin t deg. So this is exactly what I had. 2 times r times cosinus t1 deg. And now 0 to 45. And now to have x, I need to subtract a multiply by, if I have 0, then I have 0. So sin of 2 times t, because t is my input angle. And I need to subtract a by cos of 2 times t times 1 deg. Okay? Okay, you see? Let's see if it works. So you see this line here. As you have probably noticed, this line is actually now rotating. And now small digression. Why is it rotating? So it did start to rotate because accidentally this point have attached itself to the middle of the line, constrained itself to the middle of the line, and equation curves by default are not fixed to the coordinate systems because they have their own transformation matrix as all elements, and this matrix is not fixed how is it in English? Not the singular matrix, but to, I don't know this in English. So this matrix is not fixed. So when so I can actually move and rotate equation curve, and now you see equation of this curve. If I go to edit equation, didn't change, but the transformation for the coordinate systems this curve is drawn in, so its own coordinate system was changed by change of the transformation matrix for this object because I dragged it. So in other words, for simple user important explanation of this feature is that equation curves are not based in the sketch coordinate system, and they can be moved or rotated or even mirrored in the sketch without change of its equation, and then their equation does not produce the result as you would expect for the sketch. So it is important to not to drag the equation curves, and this is why I initially used the other sketch, and not to constrain the equation curves, or to constrain the equation curves in a way so the constraint will enforce the proper position of the equation curve in its coordinate in sketch coordinate system. This is more tricky, and you have to foresee what is your equation, but it is also possible. So it happens. So they are accidentally getting constrained, like in this case, to a point that traveled and for some reason, for some coincidentally was put in the middle of the curve, then it attached itself to the middle of the curve, and then the middle of the curve was dragged, and then the curve got rotated. So yeah, this is one of the, it's not the bug, it's a feature. So one of the features of equation curves in Inventor. So I will now undo few positions. Okay, I will redo that. And now you see this curve. This curve represents the position of this point while this wheel rotates. I will try to rotate this wheel without moving the curve. So if you observe, pay attention to this point. So the end of the blue line, the end of the blue line does travel on the the other equation curve actually is getting again the same. So the other point, the end of the blue line is traveling along the equation curve we had, and the other one is destroyed. So now to get the other point, we need to offset this curve by the radius. So we could calculate the radius, or I will just make a value, and I will offset this by the radius here. And this curve here now is our final curve that forms a trajectory, or actually the shape that the contact point travels. And I will now present it. So you see now the end, the other end, this end of the blue line is traveling smoothly on the yellow line, which is offset of the equation curve of the center of the lobe arc. And yeah, and this is one of the methods to use an offset function, which produces the valid geometrical result that we can use for all engineering and technical purposes in Inventor, but we do not know the equation. And if we, and the other one is totally destroyed now, so I will just, and if we for some reason need the equation for this curve, we have to then use another approach. And I will now show the other possible way to get this curve drawn, hopefully. Oh, come on.